because these are such good examples. These are such good applications. So we got Newton's law of cooling here. Newton's law of cooling tells you how quickly, when you take a pie out of the oven and you put it in the ambient air temperature on your table at 72 degrees in your kitchen, how quickly the pie will cool off. It's a pretty good approximation for how quickly things cool off. Now, this actually would work backwards as well. Like we actually could use Newton's law of cooling to figure out how quickly your pie would heat up. Like we could use it backwards, but we really never do. We use it for cooling objects. We have Project One coming up in a few weeks. Sometimes I'll have a group do something with Newton's law of cooling. Now, we can't just we're going to do the basic model today. Like we've done it. It's a homework problem. That's not project worthy. But we could modify this and maybe have an ambient air temperature that's not a constant. Maybe the temperature outside goes up and down. Like you ever watch CSI and they find a dead body and they can tell that the body has been there for 6 hours. This person died 6 hours ago. They use Newton's law of cooling to do that. They use a model similar to this, only they don't have a constant air temperature. The air temperature hasn't been the same outside over the last 6 hours. It's been going down. So we use a more robust version of this. This is real world stuff. People use this. That makes a good project. A time of death analysis. So let's take a look at this model. Let's write some stuff down. Now, one of the things that's weird with Newton's law of cooling is we've got two different T's. We've got to make sure we keep those separate. That's temperature. T is temp of our object we care about, the pie. So let's just say we're talking about a pie here, the temperature of the pie. We just took it out of the oven. And that will be K. I want to make sure I get this. Different books write this different ways. T minus A. So there's my dependent variable. Notice the independent variable doesn't appear in here anywhere. So the temp of the pie at time t, little t, is T of t. T of t. And A is the constant in this model, ambient air temperature. So we're talking a pie coming out of the oven, so we can assume that's air temp. K here is related to the specific heats or the heat capacities of the two materials, the pie that says related to heat capacities. It's actually very complicated to figure out K from first principles. What we do in general and what we're going to do in this problem is figure out K numerically by taking a couple of temperatures. Okay, this is a separable DE. It's a linear DE. It's a non-homogeneous first order linear DE. There are 3 or 4 different ways we could solve this. We have a bunch of different methods we'll learn in this class for solving this differential equation. I don't think it's exact. I mean, I guess we could write it out in standard form and check. Maybe it's exact too. Remember, a DE doesn't have to fit one mode or another. It could be none of the ones we've studied, or it could be all of the ones we've studied. But this guy is definitely separable. It's possible for me to get all my capital T's on the left and all my lowercase t's on the right. And remember, when you're doing that, you always have to move stuff by multiplying and dividing, not adding and subtracting. So what I could do is divide this over to the other side and take this little dt and move it up. Now, remember, I'll make this bigger. I had to drag it. There. Remember, the derivative here is not really a fraction. This is not really d capital T divided by d little t. It doesn't make sense algebraically. What do you mean multiply that over? It's not really a fraction. Well, it's just neat that mathematically we can pretend it is. We can pretend this is a fraction and multiply that over. I could rewrite this differential equation in what we would call differential form like this. This is a separable dE. All my capital T's are on the left, all the lowercase t's, there's only one on the right. And then we integrate both sides. And again, technically what I'm doing here is integrating both sides with respect to little t, but because of chain rule, like I go through all that in one of the videos. All that cancels out. We're integrating this side with respect to capital T, this side with respect to little t. How do we know that? Because we have our differentials there. Here, the antiderivative, we could do a u sub if we wanted to. Like if you want to go through this work, u is t minus a, then du is just d capital T. So that's the antiderivative of 1 over u du, which is natural log of the absolute value of u plus c. So over here on the left, we just get the natural log of the absolute value of t minus a. Now, that's the temperature of my pie. That's the temperature of the air in the room. The pie is never going to get colder than the air in the room. Like we just know that, right? You got a pie sitting on the table, your room's at 72 degrees. That pie is not going to go down to 50 degrees and get colder than the room. I don't have to worry about these absolute values, is what I'm saying. This one's always bigger than that one. This is always going to be positive. Most of the time, when we get these natural log of the absolute value, a lot of times we're going to ignore the absolute value, either on some physical reason and say we don't have to worry about it, or just not worry about both solutions and just take what we call the positive branch and just ignore the absolute value there. That's going to happen a lot. Okay, anyways, I'm going to put the plus c on the other side. Antiderivative of k dt would just be k, little k here. We only have a little k, t plus c. This is an implicit solution. If a question says leave your answer in an implicit form, you're done. That's it. I'm going to go explicit though. So I'm going to make both sides powers of e. E raised to the natural log of anything is that thing. Over here, I'm going to write this as e to the kt times e to the c. That's a k there. Because remember, that's rules of exponents. Multiplying like bases, you would add the exponents. And then I'm going to do something that when I took this class, burned my brain up. I did not like it. I hated this. I'm going to rename this thing right here C. Oops. See, when I took this class, I would say, okay, let's call this C1. And then I'll say, okay, I don't feel like carrying e to the c around. So I'm going to rename e to the C1. I'm going to call that C2. And this is really a different C than that one. Sure, you could do that if you want. If you want to be very, very particular, and I'm like the most particular professor you're ever going to have. I am such a stickler for making sure you write things right. And I don't even care about this one. These are different C's here. Who cares? We're going to find the value of it. We're going to solve the initial value problem. Who cares what label I put on it? Because we're going to put in a number now, right now. So don't stress about any of that. Yes, this is a different C here than what I meant there. If two different people solve an initial value problem and one person uses this implicit solution and another person uses this explicit solution and solves the IVP, you're going to disagree on what you call C. You're going to have different numbers written there and there. But if you both write it in this form, you're going to get the same answer. So don't stress about that. Okay, let's keep going here. So we get T will be A plus CE to the KT. Now let's figure out what C is by plugging in 0. T of 0 would be my initial temperature of the pie. So what is T of 0? If I plug in 0 into the function, that will be A plus C times e to the 0. E to the 0 is 1. So I can solve for C. That's what I'm trying to do. When you're solving an initial value problem, you're trying to solve for your C. So we get C equals T naught minus A. That's what C is. It's the difference in temperature, your initial difference in temperature. So then my model, this solution to Newton's law of cooling is T of T is A plus T naught minus A e to the KT. Now, what they want us to do in this problem is now use that solution. So whoever wrote this problem assumes you've already probably in class solved Newton's law of cooling. We already know I mean, you can go through this work again if you want, but this is what your answer is going to look like. Now we're going to use this to solve for K first. So I know my T naught right there. That's my T naught, the initial temperature of the coffee. Here it's coffee instead of pie. There's A, the ambient room temperature. Now we're given a point. After 19 minutes, the coffee has dropped to some new temperature. So we're going to plug in this for T naught, this for A. So your model is going to look like, see, I keep going back and forth, 65 and 177. And then whatever that number is there, right? Just find that number. Was that 112? Like, don't trust my arithmetic there, but whatever that is. Then you're given a point. You're given that T of 19 is 167. So you're going to plug in 19 for T, set that equal to 167, and you're going to have to do a little bit of algebra to solve for K. And this is what happens in the real world. Finding K from first principles based on heat capacities and whatnot, it's a real pain. It's possible, but it's hard. This is what we normally do. We let the thing cool off for a little bit, we measure a new temperature, and we experimentally find K. Then once you've got that, now you've got some model. You've got some number to plug in here for K. Now you're going to make a prediction. How long does it take? So you're solving for little t to reach 147 degrees. So the reason I wanted to go through this problem together, it's kind of a complicated problem. Separable DE, like a lot of these have videos. You're going to play a similar game that I was talking about with the rules of exponents here. You're going to split this up as e to the 3u times e to the 5t. Then you can separate your variables. Be careful in some of these questions because they ask for the answer in a different way. This does not want an explicit solution here. You're going to get a y to the 18th in your answer. They don't want the explicit solution. They want the implicit solution, y to the 18th equals a bunch of junk. And you're just writing the junk over here. They've already written that part right there for you. This is a separable DE. It may not look separable. Remember, we don't separate by adding and subtracting. We separate by multiplying and dividing. So you want to do some factoring here. Like I'm the one that added this hint in here because everybody had trouble with this problem. Do some factoring, and then you'll be able to divide something, your y's over to one side. Okay, and then I wanted to talk about this. This is similar to Newton's law of Coulomb. We call this the logistic model. We're going to look at a bunch of different population models this semester. Like you got an assignment coming up soon called the constant harvest model. It's a different population model. In fact, remember you got project 1 coming up. Some students asked me to create like a sample project. So they kind of had an idea of what the expectations were. And that's what I did. I did a whole bunch of population models. And this is one I even did in there. All right, so let's take a look at the logistic model. So this is dp dt equals, and I'll make sure it uses the same notation we got here, kp 1 minus p over m. Okay, so k here is related to my growth rate. I think we would actually call this the growth factor. It's fun. I can never keep those terms straight. It's either the growth rate or the growth factor. Don't stress about it. It tells you how quickly, say you got bacteria in a petri dish, how quickly are they reproducing? But if bacteria are in a petri dish, so you got some dish here, you can only fit so many bacteria in here. Once you reach a certain level, they're too crowded and they're fighting for resources. Anytime you have a situation like this, then you have what's called a carrying capacity. And we call that M. And this is the max number you can have before they start dying off. Not dying off completely, just you can't really go over that number because it's the maximum you can fit in your limited, with your limited resources. So that's M. It's called the carrying capacity. It's the maximum number you can have. This is a separable DE. And it's a little more complicated than what we just had. So just so I have it in front of me, I'm going to rewrite it. Again, I don't have any little t's in the equation anywhere. Look here, I only got p's. These are just parameters. Those are just numbers, the k and the m. My only variable are the p's. I could divide all these p's to the left side. I'm going to leave that k hanging out over here. Multiply, again, we're not really multiplying, but we can pretend we are. Multiply the little dt over. I've separated my variables. There aren't any little t's, but I got all my p's together on one side. Now, this is the way you see if you go look up somebody solving the logistics model. They always do it like this. And that's perfectly fine. But I find the partial fractions to be a little easier if I get rid of this m down here. So I'm going to do a little bit of algebra to get rid of this m. I'm going to multiply both sides by 1 over m so that this m will cancel here. So I'm going to distribute that in. And get that. And then on the other side, K over M dt. So I multiplied the bottoms of both sides by M and distributed here. It's not really necessary. I find I like the partial fraction decomposition a little better this way without having to deal with a fraction in here. So now we're going to integrate both sides. Technically, we're integrating both sides with respect to little t, but because of chain rule, like all that work goes on in the background. We don't have to write it. We're integrating this side with respect to p, this side with respect to t. This side's easy. We just get k over m t plus some constant c. Over here, I'm going to have to use partial fractions. So I've got this. I want to write that as some a over p plus some b over m minus p. So you saw partial fractions back in pre-calc. You did a bunch in Calc 2. You may have forgotten it. We're going to do a bunch of it this semester. It's definitely something you want to brush up on. I'm going to get a common denominator here and then set these equal. So this guy gets multiplied by m minus p. This guy gets multiplied by p. And then we have our common denominator. Now, the only way two polynomials can be equal is if all their coefficients are equal. So this top must equal this top. So we get m minus p times a plus bp must equal 1. And we want to solve this for a and b. Now, p is my variable here. So we have two different ways we could do this. We could do this by a system of equations. So I could expand all this out and write MA plus B minus M times P equals 1 plus 0P. So make sure you understand all the arithmetic I've done here. I've collected my P's together and I've collected my constant together that don't have a P. The only way two polynomials can be equal is if their coefficients are equal. So that means A equals 1. And B minus M must equal 0. B must equal M. So that's setting up a system of equations. So I'll write out that system. MA equals 1. B minus M equals 0. That's one way to solve partial fractions. Another way is what I like to call the cover-up method. What would I plug in here to P to make this 0? If I plug in P equals M, this thing becomes 0. And here I'm getting B equals 1 over M. Oh, let me pause for a second. I just confused myself. Okay, coming back a little bit. Something went wrong when I wrote down my system. So if I multiply all this out, I get MA minus PA. I had it PM here, plus BP, or I'll write that as PB equals 1. So I could do this as a system of equations. I want to think of this as powers of P. So I want to combine my P to the first together. I'm going to have B minus A times P, and then everything that doesn't have a P at all in it, MA. And that's supposed to equal 0 P's on the right plus 1. So B minus A must equal 0. And MA must equal 1. So here's my system of equations. A equals 1 over M. This says B equals the same as A, so B must be 1 over M. Now I could also do this using what we call the cover-up method, where we pick, using this form here, very particular values for our variable P to make parts of this cancel out. So rewriting this equation up here, that's a plus right there. I want to pick things that make certain parts 0. These things, I want to make them 0. So I could pick, say, M equals P, P equals M. Plug that in for all my P values. This part becomes 0. I don't have to worry about A. If P equals M, I get BM equals 1. So B is 1 over M. Or I could plug in what would make this term 0. I could plug in P equals 0. I'm plugging in for P. This would be better if I wrote it this way. P equals M. Plug in P equals 0. Then what would I get here? I would get MA plus 0 equals 1, which says A is 1 over M. We're going to do a lot of partial fractions this semester. I want to remind you how to do this. That's why I wanted to do this problem together. Okay, so we're only halfway done with this problem. That means I can rewrite this side. I had this dP over P M minus P. I could rewrite as the antiderivative of dP of, remember we're using this, and both A and B, we got 1 over M. So I'm going to get 1 over MP, 1 over M, M minus P. And I can separate this into 2 separate integrals. Now I can integrate each of these separately. The 1 over M, I could just factor out. That just comes along for the ride. The antiderivative of 1 over P dP is the natural log of the absolute value of P. We're going to ignore the absolute value here in a minute. I factored out the 1 over M. I got to be careful here. The antiderivative of 1 over M minus P dP, I'm going to pick up an extra negative sign there. I'm going to end up with a minus natural log absolute value. Again, we're going to ignore the absolute value because this will always be a positive number. P will always be less than M. This is positive, that's positive. And then what did we get on the other side? K over M T plus C. Okay, so first I'm going to clear out these M's. Again, if you go watch anybody else do this video or do this problem, most people do not bother with the clearing out the M here at the beginning. Their partial fraction gets a little more complicated. But then all the work from here on out, they don't have to do this step I'm doing now. I'm going to multiply both sides by M. So we'll get natural log of P. I'm going to drop the absolute values because we don't need them. Will be K plus C. And you're like, wait a minute, that's not C. That's C times M. M's just a constant. An arbitrary constant times a constant. It's just a new constant. Is that the same C as this? No. Do I have to label it C1 and C2? No, nobody cares. Now we're going to squish these together using rules of logs. This will be natural log of P over M minus P. T, that's a KT. Then we're going to make both sides powers of E. And we get P over M minus P equals e to the kt times e to the c. Same game we played before. And then we're just going to give this a new name. We're going to call this thing here technically a different C. This is really C3. That's a different C than that, which is a different C than that. Nobody cares. We're going to solve for C in a minute when we solve the initial value problem. All right, so we've got this implicit solution. And we could stop here. We could solve this IVP here and be happy with an implicit solution. But the question literally asks for the explicit solution. So we're going to have to solve this for P. So we got to do a little algebra here. Let's multiply this over. We have to distribute. Now I got to get all my P's together on one side, factor out a P. So I'll get P plus when this moves over. M. Factor out a P here, and I get 1 plus CE to the KT. And then I can divide that over. So P of T will look like this. It's a complicated formula. Now, a lot of books will then multiply top and bottom by e to the negative KT to make this disappear up here. So if I multiply e to the negative KT top and bottom, I'm allowed to do that as long as I do it top and bottom. This will cancel that. You get e to the 0, which is 1. And then I'm going to swap my order here. So this and this will cancel out, giving me 1 or just C, and then plus e to the negative KT. And depending on like which C we were using, you might even see different versions. We get some model that has this form. Now, what happens here? As t goes to infinity, this goes to 0. And we get Cm over C, we get P of t goes to M. That's our long-term behavior. Our population will grow up toward our carrying capacity, but then won't ever go over it. It'll just asymptotically approach it. What happens in the real world? See, we get some kind of, here's some initial amount. We'll get some kind of model that goes up like this and asymptotically approaches some maximum population. What happens in the real world is you actually go above your carrying capacity. You got too many bacteria and now they're fighting for food, so they start dying off, and you'll oscillate around. In the real world, you get something more like this, where you oscillate around that carrying capacity, go above and below it. But this model doesn't take that into account, says you never reach it. Okay, so there's your solution. You will use your initial amount, P of 0, to solve for C. So P of 0 should be 400. You have to do some algebra to solve for C. There's your carrying capacity. That's M. Oh, there had to be more information. I couldn't find it. There it is. When T equals 1, you'll have 3 times the original amount, so 1200. Use that information to solve for K in this model, just like we did with Newton's law of cooling. then you just write your model here and it's got a whole bunch of numbers in it. Like with those numbers there, this is what you would have got. Now, like I said, different people write this differently. What they've done here, you're like, wait a minute, where's that one coming from? We could divide everything by C here and rewrite this. You'll see a lot of books that will write the answer like this. Either way, it doesn't matter. Like even if you typed in something in this form and you didn't have a 1 right there, it would still give you credit. Don't stress about that. Then once you've got your model, something of this form, now figure out how long you're solving for t. You're going to have to do some algebra. Solve for t. You're going to have to take some logs. Okay, we got a bunch of exact DEs here. This is an exact DE. How do I know that? Because they told me. Remember, when you get an exact DE, your solution is always of the form some f of xy equals a constant. They don't want you to type that whole thing in here for your answer. You're not typing x squared plus y cubed equals c. You're just typing the f of xy part. So your answer is going to look something like this. And I guess depending on how you work this algebraically, you could get different answers. I would have to think about this. I don't know how we could have both of these being solutions. I have to go through and look at that. But you're not typing the equals C part. You're just typing the left-hand side.